Hello everyone, this is Mr. Collier again, and I wanted to give you another chance to see how I worked out the acceleration worksheet. So we're just going to work through this, and you can stop it and roll it back as many times as you like till you get it comfortably on your page. So first of all, it asks here, what is the formula for acceleration? And just because we're always supposed to do it, let's write it speed final minus speed initial divided by time. There's the formula. Now we have it for the rest of our time. So let's work through this. A car increases its velocity from 0 meters a second to 14 meters a second in 2 seconds. So from is initial, so that's going to be speed initial. 2 will be speed final, and of course that's going to equal time. So let's work it through. Acceleration is equal to speed final minus speed initial divided by time. Again, we always write the formula, and so we have something to work with. That is equal to 14 meters per second minus the initial, which was 0 meters per second, which means they started off from a full stop. And that all took 2 seconds to happen. 2 seconds. And if we do just the numerator part, that is 14 meters per second divided by 2 seconds. And I'm going to come up here, and I'm going to say that is equal to 7 meters per second, or 7 meters per second squared. Either of those answers, 7 meters per second, or 7 meters per second squared, is a great answer. You don't have to write them both. I'm happy with either of those. All right, number 2, a bicycle rider decreases, okay, we're slowing down, decreases his speed from 15 meters a second to 5 meters a second in 10 seconds. So from is going to be our speed initial, 5 meters a second is going to be our speed final, and this will be our time. So let's start out how we should always start out. Acceleration equals speed final minus speed initial divided by time. Let's fill in with numbers and units. So our speed initial is, speed final is 5 meters a second. And we're going to take from that 15 meters a second, which is our speed initial. And our time is 10 seconds. There we go, 10 seconds. So I like to work the numerator first. So now that's going to be minus or negative 10 meters per second. And we're going to divide that by 10 seconds. And our answer is going to be negative 1 meters per second, or negative 1 meter per second squared. Now this is the first time that we've seen a negative in front of the acceleration. So, and we know that it's slowing down. So a negative acceleration is the object slowing down. And every time we hear or read the problem that it's going to be slowing down, we know that the answer is going to be a negative number. And if you remember that, it'll really help you from making mistakes. Here we go. Number 3. A racing car's velocity is increased from 44 meters a second to 66 meters per second in 11 seconds. So here we go. Acceleration is speed final minus speed initial divided by time. That's going to be 66 meters per second. I didn't write that very well. Minus 44 meters per second. And we're going to divide all that by the 11 seconds that it took. And we'll finish that up here. And that's 22 meters per second divided by 11 seconds. And if we work all that out, that comes out to be 2 meters per second, or again, 2 meters per second squared. Again, either of those is a perfectly acceptable answer. You don't have to do both. Let's do number 4. And number 4 says, a train moving at a velocity of 24 meters a second decreases its speed to 15 meters a second over a 12-second period. Here we go. So we'll work it out as acceleration is speed final minus speed initial, and we divide that by time. And no, you're not imagining it. I just changed pens because my purple pen was running out. Here we go. Let's fill in the numbers and units. 15 meters per second minus 24 34 meters per second, and we divide all of that by 12 seconds. Again, we look up here, we see that it says decreases, so we know it's slowing down, and we hope that the number comes out to be negative. We know that's one of our truths. Here we go. We work out the numerator, the top part, that's negative 9 meters per second. We're going to divide that by the 12 seconds that it takes, and we're going to get negative 3 meters per second divided by 4 seconds, and that's going to be, because we can't leave it as a fraction, that's going to be minus 0.75 meters per second, or 0.75 meters per second squared. That's wonderful. Now let's turn the page over and see what the back holds for us. A couple more calculations that we'll do quickly, and then we will get onto the graphs. Let me do number 6. I think number 5 is hanging off the edge of the page. So number 6 is a ball rolling down a hill for 9 seconds, accelerates from 3 meters a second to 34.5 meters a second, and it does all that, of course, in 9 seconds. So here we go. Acceleration equals speed final minus speed initial divided by time. Notice how I always write the formula. Now I'm going to fill that in with numbers and units. 34.5 meters per second minus 3 meters per second, and that's all going to take place in 9 seconds. That's pretty fast. And we'll take that up here, and we'll say that's 31.5 meters per second. We just worked out the numerator. We're still going to divide that by 9 seconds, and that equals 3.5 meters per second, or again 3.5 meters per second squared. Again, either of those works. So now let's get to the sketching of the graph. The first one is the position versus time, and we're going to sketch an object moving away from the origin at a constant velocity. So here we go. Here's our axes. There's position on the y-axis, time on the x-axis, and if we know that it's moving at a constant velocity, that position versus time graph is going to be a straight line of constant slope, or as much as I can handwriting it. Now, if we look at a velocity time graph, so we're going to do the same thing. We'll draw our x and y, but on the y-axis we're going to have velocity, and on the x-axis we're going to have time. So now, if it's moving at a constant velocity, we pick some velocity, and then it's always going to be moving at that speed, so it will not change up or down. And if that confuses you, just pick a random number. Let's say 10 meters per second. So if an object's moving at 10 meters a second, and it's always moving at 10 meters a second, it's always going to be at this place on the graph. It'll just be a nice horizontal line while it's a velocity time graph. Let's go down to the position versus time. So this next one is an object moving away from origin at a constant acceleration. That means it's speeding up at a constant rate. So that's kind of like our wheel on ramp lab. So this is a position time graph. And I'll put time down here. So it's 0, 0 here. So it's going to start out, and as time goes on, it's going to go faster and faster. So the slope of that line is going to get steeper and steeper. So it starts out slow, and if we did the slope at these different points, it just gets faster and faster as we go, steeper and steeper. So, but now if we look at the velocity time graph that matches that, let's draw our x and our y. So here's velocity on the y-axis, time on the x-axis, and this shows a velocity that's increasing constantly at a steady rate. So it's going to be a nice straight line. Again, a velocity time graph, and the velocity is always increasing. That's what we saw over here. On the position time graph, if we look at that, it goes faster and faster and faster and faster, and if we look at the velocity time, it shows the velocity always going faster and faster. These two match, and these two match. And I'll leave number 5 up to you.